In this video, we'll be looking at a relatively complicated and or difficult example of the limit comparison test. Now, when starting to determine whether or not a series is convergent or divergent, we generally work through a list of possible options. The first option, very much like U sub in integration, we're going to use the divergence test. Now, I'm not going to show all these steps, but this is more or less the general guidance on how you start working through these problems as a whole. So if it tells you to just evaluate whether or not a series is convergent or divergent, these are generally the steps that you're going to want to take. Number one is attempt the divergence test. Because it's easy, it's simple, it's straightforward. You just take the limit of the thing and see if it goes to zero. If it goes to zero, well then we've got a problem. But if it doesn't go to zero, then we're done and we can conclude that it diverges. After determining whether or not the divergence test will be conclusive or not, if it's inconclusive, then we then move on to the type of series we're looking at. So this particular series, we can't determine whether or not this is a specific type of series. Now sure, it does have a k squared in the denominator, but that doesn't make this a p series. A p series is specifically a series with a constant on top or 1 on top and k to the power of a specific number on the bottom and nothing else with it. So it's not necessarily a p-series. It's definitely not geometric because it has to have a k in the exponent, and it's not harmonic nor telescoping. So the argument is that if I can determine what type of series it is, I should be able to conclude its convergency. After we've, again, knocked out those two possible options, the third option is well, can we just integrate this function? Unfortunately for this one, the integration of this would not work effectively. We'd have to do a u sub in it, and it doesn't really work all that well. The next step is for us to consider root or ratio test. But remember, with the root or the ratio test, we're looking specifically for obnoxious powers, multiple obnoxious powers, and or a factorial for either one of those cases. And in this case, there's no obnoxious powers, nor is there any factorial, so root and ratio are kind of out. We then come down to comparison or limit comparison, and I'll be honest with you, comparison test, again, is a heck of a lot more difficult or structured in a very specific, you must know the inequality comparisons, and we can actually work through the concepts of the inequality comparisons here, but we're going to try and avoid that particular case in this situation. It also comes to the conclusion that I think most of the stuff for the comparison test results in an inconclusive solution. And again, that's because of the way that we have to have the series that we bring to the table either has to be below the series that we're playing with and diverges, which I don't believe we end up making that conclusion, or likewise we have to have the inverse situation. The series we bring to the table has to be above the series that we're playing with, and then it has to converge for us to guarantee convergency. And I think in both those cases we actually have the flop, is that we have the series above and it diverges, telling us nothing, or the series is below and it's convergent and it tells us nothing. So working through all of those specific methods, we come to the conclusion that, well, maybe we'll try the limit comparison test. And in terms of the limit comparison test, we don't need to actually have any inequality comparisons with this. We just kind of have to come up with a new series that definitely has some comparison to this, and then we take the limit. We find L equaling to the limit as k goes to infinity of the series that we originally were given divided by the series that we brought to the table. Now, I'm going to go ahead and show some inequality comparisons just to help us better understand how we can come to a conclusion of something to use. So the first thing I'm going to go ahead and do is I'm going to look at the natural log of k. The natural log of k is a very unique function. It's one of those, again, transcendental functions, which is not algebraic in nature, but is unique. That right there would be the graph of the natural log function. We also have a couple of other functions we can play with. So for instance, if I look at y equals k, you'll notice that y equals k, or y equals x, is a function always above that natural log function. It's always bounding that function above. So if I were to change this natural log of k, or at least compare the natural log of k is going to be less than that of k, then when I divide both sides by k squared, we can see that these do have a concrete comparison. Now with this happening, again, we end up making some comparison tests in the vein of the problem, but we're not going to follow through with those. I'm just going to go ahead and say, well, there is some comparison between this function here and this harmonic function. So I know that then I'm bringing b sub k, the summation, equaling to the harmonic series, and because it's a harmonic series, I know it diverges always. So if I've got a harmonic series, I can go ahead and use that sequence in this limit setup. So I'm going to go ahead and look at this and limit as k goes to infinity of the natural log of k over k squared divided by 1 over k. And this will provide me with the limit as k goes to infinity then of keep flip change, the natural log of k simply over k. When I multiply this on top, the k on top cancels out with the k squared on the bottom, giving me simply 1k on the bottom. Now, when we start working through this limit, you'll notice that as k goes to infinity, the top goes to infinity, as does the bottom. This gives me the limit then as k goes to infinity under L'Hopital's rule, 1 over k on top, the derivative of the natural log of k, and the derivative of k on the bottom is just 1. So this ends up just going to 0. Well, recall the limit comparison test, and I'm going to go ahead and show this back in here, that if we equal to 0, the series we brought to the table has to converge, and that will imply that our end result series converges. So we have, well, bullocks, nothing. Because this harmonic series that I brought to the table is divergent, and we get a limit equaling to 0, that means that this whole method didn't seem to work. So we're going to have to come up with another attempt at comparing this series right here to something else that will allow, maybe we'll have convergency. Maybe the series that I want to play with or compare it to is convergency. So if I were to draw in another function here, I'm going to go ahead and use a dotted line. This is the dotted line y equals 1. So after a certain point, you'll notice the function y equals 1 is always below it. And again, it might help us for comparison. So down here, I'm going to go ahead and say the natural log of k is always going to be after a certain point. We can start ignoring certain terms. Again, remember, the convergency of a series is definitive on its infinite number of terms. And if there's an infinite number of terms, removing a finite number in the beginning of the series will not change whether or not that series converges or diverges. Again, it does change what it converges to, but we weren't asked what it converges to. We were just asked, does it converge? So I know that this natural log of k, after a certain point, will always be larger than 1. Okay, so then let's divide both things by k squared, and then this thing right here, one more time, is the original series we're playing with. So now I'm comparing this series to this series. And you'll note that this series right here is 1 over k squared, which is a p-series, and that p-series specifically converges because my p-value is larger than 1. So now I ended up bringing to the table a convergent series that I can compare it to. With this understanding that this is a p-series that's convergent, I'm going to go ahead and use that limit comparison test again, and I'm going to have a sub k over b sub k. With this right here, this is going to be the limit as k goes to infinity of, I'm going to have the natural log of k over k squared divided by 1 over k squared, and therefore I get the limit as k goes to infinity of simply the natural log of k when it all simplifies down, which actually is a problem. Because if you recall one more time, the limit comparison test specifically says if L equals to infinity, then the sum of b sub k must diverge for a sub k to diverge, and the series we brought to the table converged. So once again, we're down to nothing. So these things are showing inconclusive statements. So the things that I'm bringing to the table aren't working. I'm going to have to try something unique and something different. Well, the best way to consider this then is that didn't work. Let's go ahead and, you know what, let's try and meld this series together with this series up here. So the concept is I know that 1 over k squared is going to be a value smaller than that of 1 over k. I know this is true because, again, the value in the denominator is larger, so if 1 over something getting larger in the denominator, the overall value will then change to be this is going to be larger overall, while this is going to be smaller overall. So is there a series that I can find somewhere in the middle that maybe will help me make some conclusions of the way these things work? And the best idea that I think we have is, well, this is a power of 2, this is a power of 1, so what's something in the middle? I don't know, let's try 3 halves. So this seems like I'm pulling things just out of nowhere, and it does kind of happen that way, that you're just kind of trying things, and that's so important that just like when you were using integration strategies to try things, you're going to use evaluations of series to simply try things. I would argue that the limit comparison and the comparison test for some of the really unique cases are the most difficult examples to understand how to do, because you're just going to have to try things. It's a matter of playing with the series enough to get something that just magically works. In some cases, you might want to actually do some more research and watch more examples of how to do certain problems to see what other things other people have come up with to evaluate these, because sometimes there are numerous ways to conclude to an answer. So I'm going to try this series right here. This is the summation of 1 over k to the power of 3/2, which is still a p-series. And it's important that p-series is still convergent then. So I have a new series that I'm bringing to the table that happens to be a p-series that is also convergent. So let's go ahead and check out what L happens to be. The limit as k goes to infinity of the series that I need to conclude information about, divided by that of the series. And I'm going to cheat here. I'm just going to multiply it by that reciprocal, divided by that series that I'm bringing to the table. So again, I flipped already that series so that I can multiply those two things together, simplify this a little bit more efficiently. So the limit as k goes to infinity of, if I try to simplify this information down, I'm going to end up with something like the natural log of k divided by, well, if there's 2 powers down here and 3 half powers up here, that means that in the denominator I really have a k to the 1/2 power. So with this, as k goes to infinity, the top goes to infinity, the bottom goes to infinity, I can apply L'Hopital's rule all over again with this example, such that this top piece goes to 1 over k, and this bottom piece will end up going to 1/2 k to the negative 1/2, which I think will actually work out kind of well for us, because this, if I simplify it down, while changing this to the fractional example that it is, I have 1 over k divided by 1 divided by 2 negative exponent k to the 1/2 power. I can keep flip change all this stuff and end up with the limit as k goes to infinity of 1 over k times 2k to the 1/2 on top now, while the 1 is in the denominator because I keep flip change that, and I get basically the limit as k goes to infinity of 2 over the square root of k, which, I don't know, goes to 0 because the denominator is getting larger and larger and larger. So this provides us with the ability of saying, hey, I'm looking at L is 0. If L is 0 based on my limit comparison test, I have to have the series I brought to the table converge, and therefore I can conclude that the series that I was given also converges. And oh my goodness, it did work out. The series that I brought to the table happened to converge. The limit that I ended up with happened to be 0, and those two pieces together will allow me to conclude that this series is then convergent. So, a final statement. If I use the limit comparison test with the series 1 over k to the power of 3/2 p series that is convergent, then with the L equaling to 0, the series that we were given, natural log of k over k squared, is also convergent. And it's so important that you use those complete sentences in these examples, because it's so easy to make a statement about the series converges. If you say the series converges, what series are you talking about? There are 3 different series that I brought to the table in this problem: this harmonic series, this p series down here. So don't just say the p series either, because in this example I tried 2 different p series. It's important to be very clear. This is the series that we brought to the table. It is a p series that is convergent, and then this series here is the series that I was told to evaluate, so this series is then also convergent, given that my L equals to 0. Again, you'll notice how complex and difficult some of these problems are. It's really important that you practice the skills, manipulate the problems, and attempt new and different ways to evaluate whether or not these series are convergent. Again, this is probably the last type of method that you're going to want to use in most cases for determining if a series is convergent or divergent, but it is a method that we might have to attempt in more cases than we'd like to admit.